Hello, I'm Kirk Weiler, and this is Common Core Algebra 2 by eMath Instruction. Today, we're going to be doing Unit 7, Lesson number 4, on the horizontal stretching of functions. So in the last lesson, we looked at vertically stretching functions, and we did that by multiplying the overall function by some constant. In this lesson, we are going to look at how we take the function and, if you will, kind of accordion it. In other words, how do we compress it or stretch it in the horizontal direction? And we'll begin by trying to understand the pattern that occurs in the first exercise. So let's jump in and deal a little bit with absolute values. Okay, exercise number 1 says, using your calculator, sketch a graph of f on the axes provided. Label the coordinates of its vertex point without the use of your calculator. All right, simple enough. So what I'd like you to do is, pause the video now and use your graphing calculator to graph this original function f of x. All right, so graph this thing. Pause the video now and go ahead and do that. Okay, well, since it's our classic absolute value graph, what I'm going to do is I'm going to use my straight line command, and it will look something like this. All right, let me label that f of x. And of course, I should be able to figure out its turning point by just looking at this sort of vertex form of this absolute value function. So it's got the point 2, -3. This graph's going to get a little crowded. All right. Letter B. Consider the function g of x equals f of 2x. Determine a formula for g, then graph it on the axes. Use your calculator to find its minimum point and label it on the graph. Okay, fair enough. Well, let's find the formula together, because this is a little bit weird when you see something like this. All right, I'm going to actually do it in red, because that's how my calculator is going to graph the next function for me. So let me circle this in red. G of x is going to be f of 2x. And that's going to be 2x minus 2 minus 3. Remember, all it means is that wherever there was an x, I'm going to now put in a 2x. So what I'd like you to do now is use your graphing calculator to graph that. I would actually keep f of x in there, and then use the minimum command that we learned about in the last lesson to find the minimum of that absolute value function. Pause the video now and go ahead and do that. All right, so let's do it. This is the graph that we end up seeing. It ends up being something more like this. Nah, that's not good. Let me get rid of that. And then, of course, I erased some blue. I'm going to try to put the blue back in there. There we go. Change this back to a red. Okay, it's a little bit hard because I want to make sure that we get certain things really, really accurate on here. So we end up getting kind of a function that looks more like that. There we go. I like that a lot better. And that's g of x. And what we find is that it now has a turning point at 1, -3. Okay, now we're going to do exactly the same thing one more time. I'm going to do this in black, but we're now going to create the function h of x, which is f of 1/2 x. All right, same idea. This time I'd like you to create a formula for it, substitute it into your graphing calculator, and then graph it. Okay, well, let's come up with the formula first. So h of x is going to be f of 1/2 x, which is simply going to be the absolute value of 1/2 x minus 2 minus 3. All right. And when we graph that, we get something that looks kind of like this. And it barely, this part barely fits on. I'm going to extend it a little bit past there, even though that wasn't in our window, but we know that's the case. And although I didn't do the greatest job sketching this, I apologize. Its turning point is at f is at 4, -3. So let's summarize. F, our original function, had a turning point at 2, -3. Our next function, g of x, had a turning point of 1, -3. And finally, our function h of x had a turning point at 4, -3. So letter E, what stayed constant about the turning points? Well, that was pretty easy. The y coordinate. Right? The y coordinate didn't change at all. It was -3 each time. But what did change? Well, the x coordinate. And it changed in a way that is a little bit counterintuitive, right? When we multiplied x by 2, right, f of 2x, the x coordinate was divided by 2. And when we had f of 1/2 x, the x coordinate was multiplied by 2. Isn't that cool? Now, the only thing that's good about the counterintuitive nature of this, right? In other words, when you multiply x by 2, it actually compresses the graph by a factor of 2. And then when you multiply by 1/2, it stretches it by a factor of 2. The only thing good about it is that it's a horizontal transformation, and it's kind of working like a horizontal shift in that it sort of works the opposite of the way you'd expect. You'd kind of think, well, if I do f of 2x, then maybe every x value should be multiplied by 2. But the crazy thing is every x value is divided by 2. And when you have f of 1/2 x, it's the same deal. Even though I've done 1/2 times x, every value of x is actually divided by 1/2 or multiplied by 2, depending on how you want to think about it. All right, there's a lot sitting here. So what I'd like you to do is pause the video now, write down anything you need to, and then we'll summarize this. Okay. Horizontal transformations of functions, whether they're shifts or stretches, work the opposite of what you'd think. So take a look at this. Horizontal dilations for a real number, positive constant, such that k is greater than 1. So again, k is positive, and it's bigger than 1. Then f of kx represents a horizontal compression of f of x by a factor of k. And the function f of 1 over k times x represents a horizontal stretch of f of x by a factor of k. All right. So again, very, very counterintuitive in terms of how this should work. We multiply x by a number bigger than 1, and we end up dividing by that number. We multiply by x by a number less than 1, between 0 and 1, and we also end up dividing. I mean, if we multiply by 1/2, right? If we multiply x by 1/2, then what happens is all those x values on the graph get multiplied by 2. All right, it's kind of confusing. Let's jump into it and see how it works in the problems. Okay, let's take a look at the quadratic function f of x equals x squared minus 12x plus 20. Okay, letter A. Determine the coordinates of its turning point by using the equation for the axis of symmetry. Oh, lovely. The axis of symmetry of x equals -b divided by 2a. So let's find the turning point of this using that formula we saw in a previous unit. Let's do it together, actually. It's been a little while since we've done this. -b will be -12 divided by 2a. A is 1. So we'll get 12 divided by 2. So that's 6. So the x-coordinate of the turning point is 6. And the y-coordinate, of course, we're just going to find by substituting the x-coordinate into the formula. And we find that the y-coordinate is -16. All right, so there's our turning point of this guy. Now, letter G. or letter G. Letter B. If G is defined by g of x equals f of 3x, what should the coordinates of its turning point based on our previous work? What should be the coordinates of its turning point based on our previous work? Explain. All right. Well, since we're multiplying x by 3, this should be a horizontal compression by 3. All right. Now that means that the point 6 comma negative 16 will go to the point 6 divided by 3, negative 16. So we should have a new turning point at 2 comma negative 16. The y-coordinate won't change. Remember that last exercise with the absolute values, that y-coordinate of the turning point didn't change, but the x-coordinate kept doing it. Letter C says determine a formula for g of x and then use the turning point formula to verify your answer from part B. Great. All right, well, what is g of x then? G of x is f of 3x. So that's going to be 3x squared minus 12 times 3x plus 20. 3x times 3x is 9x squared minus 36x plus 20. So here's my formula for g of x. And let's find its turning point. X equals negative b divided by 2a. That's going to be negative 36 divided by 2 times 9. That's going to give me a positive 36 divided by 18. And that's 2. Awesome, because that was 2. And of course the y I'm going to get by just doing g of 2, by doing 9 times 2 squared minus 36 times 2 plus 20. And again, the remarkable thing about that is that it ends up being negative 16. All right, so what we see is by doing f of 3x, our x value got divided by 3, at least for the turning point, but the y value didn't do anything at all. Now letter D, which we can barely read because of all the arrows, let me get rid of some of those. Letter D says, show that the y-intercept for both f of x and g of x are equal. Why does this make sense from a horizontal dilation perspective? Okay, well, y-intercept, that's simple enough. That's when x is 0. So f of 0 is going to be 0 squared minus 12 times 0 plus 20, which is going to be 20. G of 0 is going to be 9 times 0 squared minus 36 times 0 plus 20, which is 20. So yeah, they're the same. All right. And it makes sense because when you divide x equals 0 by k, in this case 3, it's still x equals 0. Right? So the idea is, if we really wanted to produce a graph of g, what we would do is we'd take every point on the graph of f, and we'd take its x-coordinate, and we'd divide that x-coordinate by 3, but we wouldn't change the y-coordinate. There's that one point on the graph, though, where x is 0, right? So when x is 0, division by 3 is not going to do anything. Okay? Pause the video now and write down anything you need to. All right, let's get rid of this text and move on to the next problem. Actually, move on to the last problem. Exercise 3. Consider the graph of f of x graphed on the grid below. If g of x equals f of 1/2 x for all values of x, then answer the following questions. Okay, so again, this exercise is going to give us a little bit more insight into why multiplying by 1/2 is actually going to stretch this function horizontally. All right, so let's evaluate some function values, right? G of negative 6. Well, g of negative 6 will be f of 1/2 times negative 6. That's just the rule. But that will be f of negative 3. And what's f of negative 3? It's 1, 2, 3, 4. So that means the point negative 6, positive 4 lies on the graph of g, right? G of negative 2 will be f of 1/2 times negative 2, which will be f of negative 1. And that's this point down here. That's going to be negative 2. So the graph the point negative 2 also lies on this function. G of 6, well, that's going to be f of 1/2 times 6, which will be f of 3. You probably already see where we're going on here, which is negative 2. And therefore, 6, negative 2 lies on this graph. And g of 8 is f of 1/2 times 8, which is f of 4, which is 3. So the point 8, 3 lies on here. Graph G on the grid to the right. All right, well, I've got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, negative 2, negative 2, 1, 2, 3, 4, 5, 6, 1, 2, and 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3. Use my straight line command. And there it is. How would you describe this graph compared to the graph of f of x? It has been horizontally stretched by a factor of 2, stretched or dilated, right? We took that whole graph, took every x coordinate on it, and just went like this. Multiplied every one of them by 2, right? Every one of them. It's really cool, right? This point right here, which was at negative, which was at negative 3, 4, suddenly became the point negative 6, 4. This point down here, which was at negative 1, negative 2, became the point negative 2, negative 2, right? Nothing happened to the y coordinates, right? But the x coordinates kept getting multiplied by 2. Isn't that cool? All right, it gives you hopefully a little bit of a feeling for why this, just like horizontal shifting, is kind of counterintuitive. All right, pause the video now, write down anything you have to, then we'll wrap up the lesson. Okay, here we go. All right, so today we saw horizontal stretching of functions. And again, kind of like horizontal shifting, it worked the opposite that you'd think. If we have something like f of 5x, well, it would mean that we'd take every x value on the graph of f and divide by 5. On the other hand, if we had f of 1/7 times x, we would take every x value on the curve and multiply by 7. But you don't do anything to the y values. All right, we'll play around a little bit on the homework with combining these things. But for now, I just want to thank you for joining me for another Common Core Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.